we have been talking about interactability, so let me quickly go over the stuff that we covered last class and then hopefully finish this piece. This is actually the other half of the class, right? In a way, one half is the algorithm design patterns, right? It is a good thing, and by now you should know greedy divide and conquer and dynamic programming has design patterns or archetypes for algorithms. Basically, when you see a problem, you should try greedy and see if it works, right? And if not, then try divide and conquer. And if you see that you are repeating sub-problems, then you should try dynamic programming, right? And that should be something that you could, with some Google help, figure out on your own, right? And this should be part of your toolbox. The other thing is this NP completeness and all that it entails. We talked about duality, right? Which is basically, they are the same algorithm. There are two different ways of viewing the same algorithm. And the big example that we saw was max flow and min cut. They're basically the same problem. And the idea of reductions, transforming one problem onto another. So if I have to solve this other problem, I can transform it and then it's well known from then on. And that is what we're going to be using for NP completeness, which is you're doomed. Actually, you can be even more doomed, and so we're going to talk a little bit about p-space and that stuff. But NP completeness is, we don't think that there is a polynomial time algorithm. And so we are going to see what that means. There's even worse stuff. P-space is kind of the next level of ugliness. And then the infinite ugliness is undecidable. There are problems that we know, that we can describe, that we know there is no program that will solve them, which is really, really cool. And this is the same stuff that you should see, or this part should be a different viewpoint on the theory of computation class, where you will see this stuff again. The idea is, if we have a polynomial time algorithm, we can probably solve the problem. For reasonable ends, we can do Hadoop, we can do distributed computation, parallelism, GPUs, and stuff, and get it to something practical. If it's exponential, we are doomed. There's nothing we can do. We can do GPUs and parallelism and cloud, and we are still doomed. It's just, we can do n plus 2 instead of n. I mean, it is horrible. So, in practice, polynomial time algorithms tend to scale to very large problems. The constants tend to be small. We have a bunch of problems that we know that we have a polynomial time algorithm. We have some that we'll see that we don't have a polynomial time algorithm. And in fact, all of those, we believe you can't have a polynomial time algorithm. So one thing we are going to try to do is classify problems according to those that can be solved in polynomial time and those that cannot. And life sucks. There is this huge category of problems, NP-complete, which we don't know. Given that we have been trying for 50 years, we believe they can't, but we haven't proved that they can't be solved in polynomial time. And so, here's the idea. If we can solve a problem y in polynomial time, what else could we solve in polynomial time? If we can reduce a problem x to that problem y, then we can also solve the problem x in polynomial time. And that's Cook reducibility, which is slightly different than Karp reducibility. These are two different guys. So we say that a problem x reduces to problem y if arbitrary instances of problem x can be solved using a polynomial number of standard computational steps plus a polynomial number of calls to this oracle that solves problem Y. Does that idea make sense? This is the main meat. The notation is x less than or equal p, and y of x reduces polynomially to y. And just like less than, right, it is very important which side you are on, right? Just like the bathroom door is very important which side you're on. We can several things, right? We can come up with algorithms, right? If I know how to solve y in polynomial time and I can show a reduction, then I came up with an algorithm for solving x. Also, I can use it to establish intractability by going slightly the other way. If I know that x reduces to y, and I already know that x cannot be solved in polynomial time, then I know that y cannot be solved in polynomial time. Because if it was, then I could just transform and then solve x. Sorry, and solve, transform and solve y, and that would solve x in polynomial time, which would be a contradiction. And if they are both reducible to each other, we use the notation with triple bar. X is equivalent to y, and they are the same. They're either both polynomial or both not polynomial. We talked about the independent set problem, which is given a graph, can I find a subset of vertices such that, and an integer k, such that the size of S is greater than or equal to k, and for each edge, at most one endpoint is in S. So there is no edges joining two elements of this subset. We saw the vertex cover problem, given a graph, and in integer k, there are a subset of vertices such that S less than or equal to k, and for each edge, at least one of its endpoints is in S. And then we saw that they are the same thing, right? They are dual of each other. If S is an independent set of size k, then B minus S is going to be a vertex cover of size n minus k. They are basically the same thing. That's vertex cover and independent set. Then we talked about set cover. Given a set of elements, a set U of elements, a collection of S of subsets of U, and an integer k, are there a set of subsets less than or equal to k, whose union is equal to U. And then we saw that this is the exact same thing as the vertex cover. Right? Then we talked about satisfiability. You have Boolean formulas. A literal is either a Boolean variable or its negation. And rather than use ABC, we are going to use XI or XI bar, or not XI. A clause is a disjunction of literals, and disjunction means or. And conjunctive normal form is a formula that is a conjunction of classes, right? Conjunctive normal form means all you can use is conjunction at the top level, and then the next level is all disjunction. If you remember your Boolean algebra, you can play with those things and put it in any of these forms, right? Satisfiability, or the SAT problem, is given a CNF formula. Does it have a satisfying truth assignment? Can I give values true or false to x1, x2, x3, and all the variables, such that the whole formula is true? And pre-SAT is SAT where each clause contains exactly 3 literals, and each literal corresponds to a different variable. Is a slightly more, we call it constrained version of the problem, right? They are equivalent, right? If you can solve one, you can solve the other, but, or, yeah, you can express one in terms of the other, but. Tree satisfiability reduces to the independent set. And the construction they use is very interesting. Given an instance of tree SAT, we can construct an instance GK of independent set that has an independent set of size K, if and only if phi is satisfiable. We are going to do, for each clause, we are going to add a triangle, one for each one of the variables, and we're going to join. And then we are going to join every variable with the ones that have negations. In this case, we have x2 in this side, minus x2 in the middle, and x2 in here. So we're going to have a line, an edge from this x2 to this x2, and one from this to this. Does that make sense? These are actually different nodes, right? Here we have not x1 and x1 in the middle. So again, we are going to do edges that join them. So we are going to have edges from every x1 to every not x1. And the same for x2 and the same for x3. In this case, we don't have any not x3s, so there are no extra edges. Same for x4, right? Why is that? What's an independent set? What was an independent set? At most, one of its endpoints is in S. So what's going to happen here? I'm going to have one of these appear, and then I cannot have x2 and not x2 together, right? Either x2 or not x2. So that's what this is. Our lemma is that G contains an independent set of size k equals phi, size of phi if phi is satisfiable. So let's see, let S be an independent set of size k. It needs to contain exactly one node in each triangle, right? And so by setting those variables to true, and the other variables to who cares, right? As long as they are consistent, we are gonna get, right? Each one of those is either, right, x, not x1 or x1 is gonna be true, and then I cannot have an x1 and a not x1 together, because of the extra edges that I did. So by setting up one of those, I will get, I cannot get two in the same triangle because I have this edge, right? So I have to get one from each triangle. And then I cannot join I cannot have contradictory assignment values. So that will be a truth assignment that satisfies the conjunction. Given a satisfying assignment, I can select one true literal from each triangle, and that gives me an independent set of size k. So we have seen simple equivalents. They're basically the same thing. Vertex cover is a slightly slightly less general case of set cover. So seeing how to do that. And then these things are called gadgets. These weird constructions, right? Like the triangles in this case. And so if we encode with gadgets, we can do those things, right? We have less than or equal to p, or polynomial reduction is transitive. So if x reduces to y and y reduces to z, then x reduces to z. I can just combine the two algorithms, right? And so I could say that tree sat reduces to set cover by going through independent set and then vertex cover. Now, slightly different variations of the same problem. Decision problem. What's a decision? Yes or no, true or false, right? So a decision problem is there a vertex of size k? Or is there a solution of size x, right? A search problem is find a solution of size x. In this case, they're talking about vertex cover, so, and I can go from one to the other. If I have a solution to the decision problem, right? Is there a vertex cover of size k, right? And of course, if I have solution to the search problem, then I have solution to the decision problem, right? So if I have solution to the decision problem, how can I solve the search problem, right? Well, I can eliminate one vertex and see if I can find a solution of size k minus 1. If I do, right, then that guy is in my solution of size k, right? And I can recursively go through that. How long does this take? Potentially n squared, right? It could be summation of n minus 1 and minus 2 and that kind of stuff, right? But it's still polynomial. Does that make sense? It takes me a lot longer, but it takes me polynomially longer. So I'm not that doomed. Optimization problem is even harder. It is find a vertex cover of minimum size, right? Or find a solution to problem X of minimum size. I can do binary search for that minimum size, right? And then solve the search problem. And again, the k is related to the size of my problem, right? So it's log of the size of my problem. Right? not going to, or some polynomial thing related to the size of my problem. Does that make sense? So even though optimization is a lot harder, if I can do one polynomially, I can do the other.
Is equivalency is on the bottom line is not, right?
Yes.
Is that just for this
No.
example, or is it in general?
It's in general.
It's a decision.
Decision.
To search is equivalent to optimization.
Yes. In terms of polynomial.
Okay.
It doesn't mean that they take the same time.
Right.
But if you, and you have to be slightly careful in that the case have to be polynomially related to the size, right? So normally k is capped at the size of your problem. But it may be, right, you can come up with different definitions. So as long as your maximum k is a polynomial function of your size. It could be size squared, it could be size cubed. As long as that happens, then this will hold. When you're talking among friends, you just say this will hold. When you are being careful, then. Sorry?
My friends aren't that smart.
You don't talk about this stuff with friends, man? Especially after some rum. A lot more candy. Hamiltonian cycle. Given an undirected graph with vertices and edges, is there a simple cycle that contains every node in V? Simple as in you cannot use an edge more than once. It's easy to see on something like this because they put it pretty. When you see something like this, you say, oh God, right? How can you brute force this? Find all the what?
The simple cycles.
Yes, find all the simple cycles, right? How much simple cycles there could be? A lot. Potentially 2 to the n, right? Which is all the possible subsets of these sets. 2 to the size of b or something like that, right? I can show that directed Hamiltonian cycle reduces to the Hamiltonian cycle by doing this cheating thing. Create 3 vertices for each vertex, call it in, V, and V out, and then join the out of the other guys to the in of your vertex, and vice versa, and do that all over. You end up with 3 times the number of nodes, but now you end up with an undirected cycle, and if you have a directed cycle, right, then you can just do the undirected cycle by following the exact same thing in the same order. If you have an undirected cycle, then by looking at this, you're either you have to be alternating blue, red, white, right? So you're either going blue, red, white, or you're going, blue, red, white, blue, black, white, or white, black. So just check which way the actual things go, and that's the equivalent one. So you're either getting a directed cycle or a reversed. So just make it go the right way, and life will be good. Now, let's destroy our sanity, our collective sanity. Let's show that 3 SAT reduces to directed Hamiltonian cycle. So, given an instance of 3 SAT, we will construct an instance of directed Hamiltonian cycle that has a Hamilton cycle if and only if that instance is satisfiable. So, what are we going to do? We are going to have a graph that initially has a ton of cycles. Given that you have n variables and k clauses, we will put our variables in rows, and we will create 3 times the number of clauses. We will create actually that plus 1 on the other side, right? Or going from our row. So in this case, we have 3, 4, 5, 6, 7, 8, 9. So our k was also 3. No, our k was 2, right? We have two conjunctions. We do create 2 extra nodes, S and T. We go from S to X1 on both sides, and from X1 to S, from each one of the 2 X1 nodes on the extremes, we can go to the X2s, either directly down or across, and the same for X2 to X3. So in here we could have a gajillion cycles, right? Actually, not that many, but we could come here to X1, then go all the way down, right? So we have 2 choices, 2 choices, 2 choices. So we have 2 to the n ways of going from S to T. Right? We have 2 ways to get to X1. We either go to the left or to the right. Then we'll go all the way to the other side because we need to get every. And if we're in the middle, we just have to keep going, right? You can't come back. So we just go all the way to the other side. And then again, we have 2 choices. And then we are going to do horrible stuff. This is the gadget that will we will create, and how was it? Oh, yeah. If we have X1 positive, right? We are gonna go. We'll create a node for each clause, and then for each one of the variables, if we had the variable positive, we will add. This is for X1. We have this line, and then this line that comes to the right. So making the variable positive means we are going this way. Once we do that, right, it has to stay that way, right? So if we had other clauses with the same variable positive, we can do that, and so we can go and visit that node. However, for in C2, we have not X1, and so it actually goes the other direction. When you go and come back, you end up in the other direction. This makes sense. Just look at x1, right? Or at the row for x1. If I enter this C1, right? It's this guy on the blue. If I enter this C1, then when I come out, I'm towards the right, which means I have to keep going this way, right? If I'm coming from that direction, I have to keep coming this way, and I cannot enter C2, which has the negation, because that would put me backwards, and I will need to pass the same edge again. Does that make sense?
No. I mean, I feel like we went from, why are we going along the path? I guess that's where you lost me. Where did we go from?
We want to create a cycle,
Okay.
right? We want to create a cycle. So let me go to the previous one. Thanks for doing this. Thanks for asking the question. Instead of just nodding. If I want to create a cycle, right, from S to T, and then I have this edge that goes back to S, right? So I have to start an S. I can go either to the right x1 or to the left x1. Does that make sense?
Yes.
Okay. Imagine that I went here to the right x1. That to my right x1, to your right as you're looking at the page or the screen. Then I have to go all the way to the left on this row. Does that make sense? To make a cycle.
Is that possible to go down to x2, right?
If I go down to x2, I'm doomed. I will never visit all those things.
Oh.
So I will never have a cycle that uses every node.
Okay.
Right? I need a cycle that uses every node. Right? And so if I ended up in this x1 to the right, I have to go all the way, right? Now, once I do that and I end up on the left x1, then I can either go down or go to the left x2 or go all the way to the right x2, right? And imagine, let's say that I go down, then I will need to go all the way to the left. There is probably ways to do tools, right? Tools. Can I annotate and draw lines? So, this is a line. That's a horrible line. That is a horrible, horrible line.
There's a pencil tool.
That's text. Not the right thing. This guy?
One to the right. One to the right.
This guy.
No.
Other way.
The other right.
Yeah.
Okay.
Yeah, I think you need to change your color.
Yeah, to like the weekly
This guy?
one. No,
This guy.
One more.
This one. Ah! We have a line-ish. It is the ugliest line ever. I cannot draw straight, even with a.
We get the point.
Delete this guy. Then tools, annotate, line, control, Apple I. Ah! So now I need to go.
to x2.
No.
Oh.
If I go to x2, then I can never go back to x1, right? Because all the lines go from the x1 row to the x2 row. So if I ended up there, I have to go all the way to the other side.
So you're visiting x1 2 times because you got x1 right here and x1
Well,
right there.
I have 3, 6, 9 nodes for the x1 row. I have x11, x12, x13, right? So I have to go through all of them, right? Once I got here, then I could go which ways? Can either come down directly.
Or go to X2.
Which way do we want to go?
Down.
Directly down. Cool. And now, if I'm here, which way do I have to go?
Right.
To
All the way across, right? And then what do I do? Down or up?
Well,
Down or across?
across.
Across.
Right.
right.
And then I have to go right, right?
Right.
Have to go right, right? Left, no. Right? And then I have to go down to T and back to S. Does that idea make sense?
Okay.
How many different ways do I have of doing this stuff?
About 8.
8, right? 2 to the n. Because I have 3 variables. Does that idea make sense?
It was when we added the blue squares and like the
Now,
extra bits.
The blue
let's
square
go
does.
add the blue squares. Ah!
Yeah.
Let's go
those
add the
parts.
blue squares. Actually, let me do this to highlight. Let me change this color to be something other than blue. How about red? Cool. And can I? Let's look at x1. I have this guy, right? And then I have this guy for my clause. Does that make sense? And I'm purposefully not going all over so you can see the arrows. Maybe next time I teach this class, I'll figure out how to draw arrows. I'm never teaching this class again, so. For C2, I have this one.
So were these clauses just thought up for this example? Like they don't have any.
Well, they are the closest of my problem, right? This is the problem that I'm putting an equivalent one, right? Except that they're just giving me this example.
I guess my question is. Wait a minute. All right, never mind. Go ahead.
So, what happens with this, right? If you notice, for C1, x1 is positive. So I am going to the right. So in order to visit x1, right, I have to move to the right. In order to visit, x1 on C1, right? In order to visit C1 through x1, I have to move to the right. And that says x1 is going to be positive. On C2, I have not x1, right? So it forces me to go to the left. If I visit C1 on the x1 row, then I cannot visit C2 because that will force me to repeat an edge. Does that idea make sense? Yes? And so that is what makes, right? Well, if I have a Hamiltonian cycle, then I gave, right, I have to go visit C1 and I have to go visit C2, right? But this weird contraption, this weird gadget thing, makes me not be able to assign contradictory values to x1 and x2 and x3. So if I'm able to find a Hamiltonian cycle, then I can find, right, what did I do to x1? What did I assign to x1? And what did I assign to x2 and to x3? And maybe that I don't care because I visited C1 one way and C2 the other way. So I don't care what's like, maybe I visited C1 on x1 and I visit C2 on x2, and then I don't care what's x3.
So could those blue boxes be shifted to the left or right as long as the same rules apply?
Yes, but they are leaving one in the middle.
Okay.
Right? So as long as you leave one in the middle, yes.
Okay. That makes a lot more sense.
So in the x2 case on C1, you forced to go to left. All right.
On C1 x2, let's
X2.
see. C1 x2 is going from here, yeah, it's going to left because x2 is negated. And actually, it is also negated on C2, so that's an easy one, right? But that's an easy one because I'm looking at it, but I just roll the die that gives me a Hamiltonian cycle. I just call the get Hamiltonian cycle procedure, and I don't care what it takes. So if I have a Hamiltonian cycle, I can get to values of x1, x2, and x3 that would satisfy this thing. Does that make sense? And vice versa, given values of x1, x2, and x3, right, I can give you a Hamiltonian cycle. So I can tell you how you enter. Does that make sense? So tree satisfiability reduces to Hamiltonian cycle with a horrible, horrible way. That is actually the easy one. There is an uglier one. There's a couple of uglier ones. Tree sat also reduces to longest path, right? Longest path is there a simple path consisting of at least k edges, right? Hamiltonian cycle is basically longest path, except take out the last one, right? And so tree sat would reduce to Hamiltonian cycle, and so to longest path. Yeah. There is, sorry?
That's at Verizon.
Yeah. This is probably the most famous combinatorial optimization problem. The traveling salesperson, TSP. It is a slightly idiotic problem, but it's actually reasonable, right? Imagine that you're a traveling salesman or traveling salesperson. You want to visit a bunch of cities, right? And you want to visit the cities once. You don't want to go through them again, right? So it's like, well, every week I need to visit these 7 cities, right? How can I travel to make a circuit, right? So that I visit each one of them with the least amount of distance. And so we have a set of n cities and a pairwise distance function that tells me the distance between two cities. So given that, what's the shortest possible tour, or is there a tour of length less than or equal to some distance, right? And this pairwise distance function is a complete graph, if you want to look at it that way. It's a graph where each one of your nodes, your cities, is connected to each other, right? Does that make sense? You're trying to minimize the distance.
That poor salesman.
That poor,
Oh,
yes.
salesperson.
That poor gal has to travel all over, right?
Just every.
That makes my head nervous.
Yeah. This, right, has actual applications in a bunch of optimization things, and actually a bunch of optimization problems reduced to the traveling salesperson. Stuff like network connectivity and things like that, right? In this case, it's circuit design. So the traveling salesperson is given a set of n cities and a pairwise distance function duv. Is there a tour of length less than or equal to d? And the Hamiltonian cycle reduces to the TSP. How can we do that? Well, given an instance of the Hamiltonian cycle, right? Create a TSP problem with one city per vertex, and then my distance is going to be 1 if there is an edge, or 2 if there is no edge. And so if there is a TSP of length n, I'm going to have a Hamiltonian cycle. If there isn't, then I don't, because I have to go through at least one with a distance of 2, which means there is no edge. What happened to my... started working. So now we have seen that TreeSat reduces to all of those guys, right? Isn't that cool? Partitioning, 3D matching, given n instructors, n courses, and n times, and a list of possible courses and a list of possible times per instructor, can we find an assignment so that all courses are taught at different times? So I have to be doing triples. The math version of this is given 3 disjoint sets, x, y, and z, each of size n, and a set T subset of all the possibilities, x and y and z, of triples. Is there a set of n triples in T such that each element of x union y union c is exactly one of these triples? One professor, one course, one time. It's a generalization of bipartite matching, and you thought the other one was ugly. we can create a tree set from the 3D matching. Actually, the other way around. We can create a 3D matching from a tree set, sorry. To show the tree set reduces to 3D matching. And here's the really cool thing. We are going to create a gadget, right, for each variable xi with 2k, twice the number of clauses, core, and 2k tip. And I alternate colors, blue and gray. The core ones get joined, and the tips are available. What's going to happen, right? If I choose blue, right, that eliminates these two guys, right? It would let me choose, right, the other blues. So basically, once I choose blue, I'm blue forever. Once I choose gray, I'm gray forever. But it's not necessarily true yet. That's going to be the idea, right? I'm going to have false and true. So for each clause, I'm going to create a tip. I'm going to attach to a tip, and I'm going to have here my two nodes, and now these are ugly as hell, right? Basically, once I have one, I don't choose the other ones, right? So I only need to choose either this false or this true. Actually, the other way around, right? Either plus one is x1, or I think these things are actually, well, it doesn't matter. It's true or false, right? And then there is gonna be tips that are not matched, and so I create purple cleanup gadgets that do the remainder cases. Now this is ugly as hell. It works, but it's ugly as hell. So basically your colors, right, become your, this is the, what the heck is this? Basically, each one of these clauses is going to have one in white, one in blue, and one in black. So, if you find a 3D matching, then assign xi according to the gadget xi. And if I satisfiable, use any true literal to select the gadget that's going to be there. So this is joining this tree, right? So it's either these or these or these, which is the equivalent of there. This should destroy your brain. I think there's even an uglier one. Um, there's another one in here, just for fun. I solemnly swear I will not ask you to do this one. It is a good idea to understand the general technique. It is a good idea to be able to produce a bunch of them. It is not necessary to memorize all of them, especially the really old, because that's what books are for. But knowing the techniques, right, and understanding the examples will give you the ability to. God, I don't think you'll be producing these things on your own, but at least having a good chance of Googling stuff and understanding Google proofs of this stuff. If you ever use this in your career, please send me an email. I'll be very, very interested in knowing. Other than research papers, right? But it's a very good idea to be able to say, oh, this is an NP complete problem, so don't worry about solving it. It's not going to happen, right? So being able to say that is good. I've never seen one that wasn't a well-known problem that I could just Google and verify that it's NP complete or not. But graphic colorability, given a graph, can the nodes be colored black, white, and blue so that no adjacent nodes have the same color? This is tree color. A big application of this is register allocation for compilers. Those of you who everybody took computer architecture, right? You know that machines have registers, processors have registers, and the data in the registers is even faster than any access to RAM, right? They are just uber fast. And so if I can put all this stuff for solving an expression, if I can put all this stuff in registers and play with registers, then evaluating that expression is going to be faster, right? Because I'm not going to RAM. And so register allocation is a compiler technique that says, oh, let me assign variables to registers, variables in your program to registers in here to try to make this stuff faster. And I will stick this variable into this register, and for the life of the variable, use the same register and never or only access memory at the very beginning, and then keep using the same register. In order to do that, you can create an interference graph where the nodes are the program variables and the edges is, there is an operation where both of them are live. That is, their scopes intersect, right? And Chaitin, or however his name is pronounced, proved that I can solve register allocation if the interference graph is k colorable for k number of registers, right? And we know that tree color reduces to k register allocation for any constant k greater than 3. And that's kind of obvious, right? Tree color is tree register allocation, right? We are going to show that tree SAT reduces to tree color. Given a tree SAT instance, we will construct an instance of tree color that is colorable if and only if the instance is satisfiable. So we are going to do horrible things again. We'll create a graph with a node for each literal, connect each literal to its negation. We are going to create 3 new nodes, TF and B, connect them in a triangle. Connect each literal to B and then for each clause, add a gadget of 6 nodes and 13 edges. You didn't get the right one. So that
Yeah.
one? No. This one, right?
There we go.
This is the one that we're not going to see. You believe me? Cool.
good.
Sounds good. So we have seen even more problems, right? That tree set reduces to. And it actually, the planar tree color, and there is even more stuff. Some interesting numerical problems. Subset sum, sorry. Given a bunch of numbers, a set of numbers and an integer w, is there a subset that adds up to exactly w? Just to be slightly more precise, we will assume that integers are encoded in binary for doing arithmetic problems. So you're doing the size in, the size is the number of bits in binary, right? And tree sat reduces to subset sum. In horrible, horrible ways. We will create integers. We have our variables and then our clauses. We have one row for x1 and not x1, right? And here we will put the so C1 is gonna color the ones that it includes. So not x1, x2, and x3. So I create this, right? x1, x2, x3, and then C1, C2, and C3 will be whichever one they occupy, right? And then I create dummies so that the columns add up to 4, except that they don't. They actually add up to 2 here. They guess this should be 4s, right? Sum of which Cj digit is 4. Wait. Oh, never mind. I only no. This is wrong because that doesn't add up to 4 in any way, shape, or form. Two, 3, 4, 6. Make this zeros, then they'll add up to 4. what they're doing is some horrible thing. This is just like, what? Wait.
So we can assume this won't be on the test.
Okay, assume this won't be. I will go find out exactly what they were thinking. 'Cause, yeah, this doesn't. They don't add up to 4. I will tell you what is the trick, but for now it won't be on the test. There is a couple of other problems that I'm leaving as an exercise to the reader. Partitioning, which is similar to subset sum, scheduling with release times, and that kind of fills up this. And just so you know, some poor guy, Carp, came up with this stuff at the time where they were still typewriting their program. In maybe 60s or 70s, found, right, and this is kind of a famous set of NP-complete problems, 21 NP-complete problems. And once you have a few, then you can just go through and prove to any of these, right? So that makes it a much easier task. And I will see you guys on Wednesday, when we'll keep doing this, but now talk about what it entails, and P and NP and all those things, which is actually really cool.